ಸೆಟ್ಟಿಂಗ್ ಅಪ್ ವೆಬಿನಾರ್ ಫಾರ್ ಯೂಟ್ಯೂಬ್ ಲೈವ್. ಒಂದು ನಿಮಿಷ ಆಗ್ತಾ ಇದೆ. ಆಯ್ತು, ಯೂಟ್ಯೂಬ್ ಆಯ್ತು. ಓಕೆ, ಮ್ಯೂಟ್ ಮಾಡ್ಬಿಡ್ಲಾ? ವಾಲ್ಯೂಮು. ಓಕೆ ಸರ್. ಮಾಡ್ಕೊಂಡೆ. ಪಾಸಾ? ಓಕೆ. ಓಕೆ, ಝೂಮು. ಓಕೆ, ಬಂದೆ. ಹಾಂ, ಈಗ ಸರ್ ಹೇಳ್ತೀನಿ. ಇಲ್ಲಿ ದುರೈ ಆನಂದ್ ಕುಮಾರ್ ಮತ್ತೆ ಸೆಲ್ವಿಕಾ ಮಲ್ಲಿಕ್ ಅಂತ ಇಬ್ರು ಇದ್ದಾರೆ. ದುರೈ ಆನಂದ್ ಕುಮಾರ್, ಮತ್ತೆ ಶೆಲ್ವಾ ಮಲ್ಲಿಕ್ ಅಂತ ಇಬ್ರು ಬಂದವರು. ಶೆಲ್ವಿಯನ್ನ ಹೋಸ್ಟ್ ಮಾಡ್ಲಾ? ಓಕೆ ಸರ್, ಆಯ್ತು. ಸರಿ, ಅವರನ್ನು ಪೋಸ್ಟ್ ಮಾಡ್ಲಾ? ಆಯ್ತು, ಸರಿ ಸರಿ ಸರಿ. ಈಗ ಓಕೆ ಓಕೆ, ಸರಿ ಸರಿ, ಆಯ್ತು. ಸರಿ ಸರ್, ಪರವಾಗಿಲ್ಲ. ಇದು ರೆಕಾರ್ಡಿಂಗ್ ಈಗಲೇ ಆಗ್ತಾ ಇದೆ. ಆಗ್ಲಾ ಕಾಲಿ? ಓಕೆ, ಸರಿ, ಆಯ್ತು. ಸರಿ, ಅದು ಬಿಟ್ಟು ಪರವಾಗಿಲ್ಲ. ಏನೋ ಇದ್ರೆ ಫೋನ್ ಮಾಡ್ತೀವಿ ಸರ್. ಬಟ್ ಒಬ್ರಿಗೆ ಬಿಟ್ಟರೆ ಕೋಸ್ಟ್ ಮಾಡೋಕ್ಕೆ ಇನ್ಯಾರು ಇಲ್ಲ ಅಲ್ವಾ? ಇಬ್ಬರೇ ಇರೋದು. ಓಕೆ, ಆಮೇಲೆ ಇನ್ಯಾರನ್ನ ನಾನು ಅಡ್ಮಿಟ್ ಮಾಡೋ ಅದೆಲ್ಲ ಏನೂ ಇಲ್ಲ ಅಲ್ವಾ ಈಗ? ಯಾಕಂದ್ರೆ ಆಯ್ತು. ಆಯ್ತು, ಸರಿ. ನನ್ನ ನಂಬರ್ ಕೊಟ್ಟಿರ್ತೀರಲ್ಲ ಸರ್, ಅವ್ರಿಗೇನೋ ಬೇಕಾದ್ರೆ ಕಾಲ್ ಮಾಡೋಕ್ಕೆ. ಅದೇ ದೊರೆಸ್ವಾಮಿ ಅವ್ರಿಗೆ ಯಾರು? ಡನ್ ಸರ್. ಓಕೆ, ಬಾಯ್. ಸಾಯಂಕಾಲದವರೆಗೂ ನಿಮ್ಗಿದೆ ಊಟ? ನೋಡು ಪಾಠ ನೋಡ್ಕೊ. Very good morning, yeah, please. Now you're talking to me an IT person. I'm an IT department person. Better. Satish. No, I tell you what it is. See, I'm in university. You have to talk to college people. You'll come to me. Fine, no problem, no issue. Okay, bye. The mountain was lonely because it crashed. It had no friends. We were tired. Answer, Rama. ಹಲೋ.
Hi, Shelvia.
Hi, Prajwal.
Okay, that's great. I just wanted to check if it is audible.
Yeah, it's much better today.
So the streaming is on.
Yes, it's live on YouTube right now.
Okay, great.
Good morning and welcome everyone for day 3, phase 1 of Indian webinar series Introduction to Computational Drug Design, co-organized by Schrodinger and PCI. As every day, we have 2 lectures lined up today. The first one is Theory, Principle, Methods of Molecular Docking by Dr. Prajwal. And the second one is virtual screening to prioritizing the molecules. I think we can start the first one, Dr. Prajwal.
Yup. Yup. So shall we start?
Yes.
Okay, great. So let me share the screen first and then we'll proceed further. Mm, yeah. So, what about now? Are you able to see the screen?
Yes.
Okay, great. So I'll just hide that panel and it should be fine. Okay. So I hope it is okay now. Can anybody confirm?
Yes, it's visible.
Okay, great. So yeah, good morning to all of you guys. And again, I'm back. Thank you very much for joining the presentation and this webinar series. So, okay, before starting the presentation, as I said, like you can note it down my email ID and mobile number if you have further queries or if you want to have further discussions. So that will be fine. And so today we are going to discuss about the binding site prediction, or how to analyze the binding site which is present inside the protein for ligand binding. So for example, whenever we talk about computer aided drug designing, and for that one of the most popular method is molecular docking. And the whole drug designing revolves around how drug molecule binds to the protein target. So wherever it binds, that region we call it as a binding site, which is present in the biomolecule, for example proteins, DNA, RNA, or antigen, antibody, or any type of big molecules. So it is very much necessary to know about that binding pocket before proceeding for any type of molecular modeling studies. So considering it as a fact, so today we will discuss all those aspects of binding site analysis and predictions in very much detail. So again, one more thing which need to remember is in Schrodinger we have a very nice tool called as sitemap. So basically it will help you in doing binding site predictions and further analysis of it. So at this point it is worth to remember just a name of module, which is sitemap. So considering the analogy of drug receptor binding, if you see, like, it follows the lock and key model, and basically your biomolecule like protein is considered as a lock, and the drug molecule or any inhibitor molecule, whatever we are studying, are basically key, and that follows this lock and key model. And whole idea about is how it fits inside the binding pocket of protein, means how key fits inside the lock. So it suggests that lock, though lock looks like even or uneven surface, but still it has a definite position where only key can fit inside it. So that's the same thing which is follows for drug receptor binding. It has a particular space where it gets fit inside it. So if you come to know about that space, which we call it as a binding site, and if you know about its property, then you can easily design a key for this particular binding site. So the same idea follows, and the thing is we need to understand how this lock look like inside that particular lock where key can bind. So this is one of the video of very revolutionary study in that time. So this study is published in 2011 in Journal of American Chemical Society by D.E. Shaw Group, and that time it was really revolutionary study which was published. And what it shows the basically exploration of various sites which are present in the protein by a ligand. So basically ligand is exploring lot of different sites in which we can see how it looks like. I'll just try to play it. Yeah, so you can see here basically this is the protein structure in surface view, and whatever is jumping around in this orange color stick is a ligand molecule, basically a inhibitor, or you can say it as a drug molecule. And if you look carefully, the whole protein is having very much uneven surface, and it is not at all like static. So all surfaces are getting changed with respect to time, and it also forms various small binding cavities, various big binding cavities, and there can be many different various pockets which are being formed during the course of simulation. But at the end, during whole simulation, drug tries to explore various small pockets, various possible pockets inside the protein, and finally it get fits into the particular pocket where it is a stable enough. So this pocket we call it as a binding pocket. This is what is the specific pocket which is present inside any protein where a drug or inhibitor can bind. So this is what is all about knowing about the binding pocket. So whole exercise we need to do to identify that specific thing. So if you see with respect to the lock, we need to identify that particular region where key can fit inside it. And other important thing is like key doesn't fit anywhere else. So it fits at particular position or a particular space, which we call it as a binding pocket, because of some reasons. And what are those reasons? So that reason is because in that particular region there are many properties like hydrogen bond acceptor property, hydrogen bond donor property, or hydrophobic region are present inside that particular cavity. And when it all comes together, and it creates a favorable environment for a ligand molecule to place perfectly inside that binding pocket. So for example, here it is shown in yellow region is a hydrophobic cavity or hydrophobic property of receptor which is present. So basically if ligand molecule has some hydrophobic ring structures, it can perfectly fit inside this yellow color region. So it somehow holds ligand molecule inside the binding pocket. Not only that, but there are some hydrogen bond acceptor groups, there are some hydrogen bond donor groups, which basically keeps that ligand tightly hold inside the protein structure. And this is what, whenever all those things come together, it makes all favorable conditions, and that's why this particular region of the protein, we call it as a binding site, because it is able to hold the ligand molecule inside that particular pocket. So whole idea is about identifying that particular region inside the protein structure. So if you see the overall protein structure in this left hand side image, which is a representation in very much traditional view, which we call it as a cartoons view. So in cartoons view of a protein structure, if you see, it is, it doesn't show you various binding pockets or whatever is present inside the protein. It just show you a integrated protein structure, so that you can get an idea. Yes, protein structure is here, these are the alpha helix regions, there are some beta sheet regions, there are some loops region, means protein structure is present. But if you want to see where ligand can bind, or where are the various binding pockets are present inside the protein, the better view is surface view of this particular protein structure. So whenever you see this such a protein structure in surface view, you will see like it's not at all a even surface. It doesn't look like a plain circular region or plain rectangular box, but there are many lot of uneven surfaces are there, many small pockets are there, a lot of creased and tufts are there. So it means there are many such regions where ligand can fit inside it based on the size of that particular region. For example, here at this particular place where the small pocket is there, means small molecule can fit inside it. It may fit somewhere here, it may fit somewhere here, and it might also fit somewhere here. So it all depends on whether it all follows those various properties which we have discussed, like hydrophobic property, hydrogen bond acceptor property, or hydrogen bond donor property, whether all those pockets make a favorable environment for ligand to be placed inside the pocket or not. So just by looking at this uneven surface, I can see there are many small pockets are there, but which one is the actual binding pocket? So when that question comes, and if I see in detail, like I can see for this particular structure, ligand is specifically present inside this middle binding pocket, which seems to be large enough. And here ligand is shown in ball stick view, and this ligand is also present inside it because it has this particular binding pocket has all those properties to hold this particular ligand. So that's the reason why ligand is not going anywhere else inside the protein structure, but it successfully goes inside this middle binding pocket, and it stays there for a long time, and ultimately because of that ligand binding, it gives you the biological activity for this particular ligand molecule. So this is how we can explore various pockets which are present inside the protein structure by using visual analysis. But as I said, each lock has a definite region where key can fit. So same analogy works for the protein. It has a definite region where your ligand can fit. So the idea is about, once you come to know about, yes, there is a definite region, so let's explore it. So whenever you try to explore this particular region and see it in a more detail, you will find like this particular big binding pocket also has lot of small sub pockets. Means you can see specifically here, this is what is the small sub pocket which is present inside this big binding pocket, and the region of some ligand, sub few of the atoms of ligand are also placed inside it. The same thing is followed in even this big binding pocket. There can be many sub pockets where the portion of ligand can fit, and collectively it gives you all that effect which leads to the perfect fitting of ligand molecule inside the binding pocket. So if you see it in a surface view, you can see there are many those pockets which are pockets or sub pockets which are connected through a small tunnel region. Means you can see like ligand is fitted inside it, but it doesn't ends the story. Your binding pockets also extend little bit, and it also connects to the various sub pockets like transient sub pockets which are present far from the ligand binding pocket through some small tunnel. And basically it, what does it means? It means that though ligand fit perfectly inside the small portion of a big binding pocket, but still there are many unexplored regions which are present in this big binding pocket. So we need to study that, what does it mean, or how we can use it for the further drug designing. So for example, let's see in this particular view, where the protein is present in cartoons representation, you can see how big the pocket is. But when we see it in a detail, you will see like this big binding pocket which might have a lot of small sub pockets, and here ligand is shown in space field view. And this magenta color carbon thing is a ligand molecule, and you can see easily this particular ligand is just occupying small portion of big binding pocket. Still there is big region of a binding pocket which is not explored by any other ligand. So what does it gives me? It gives me basically a opportunity to design my ligand in such a way that it could even occupy the rest of the binding pocket and can have a better fit than the existing ligand. So imagine, for example, this particular ligand which is present inside this particular binding pocket has activity of 10 nanomolar because of the perfect binding in this particular region of the binding pocket. But if I want to proceed further, I want to get more activity than 10 nanomolar, and I want to design it further, I would design it in such a way that it will occupy rest other portion of this binding pocket, so that it also gives you more tighter binding. So if there will be more binding, there might be a more biological activity. Means biological activity might extend from 10 nanomolar to 1 nanomolar or zero 0.1 nanomolar. So that can be a 10-fold or 100-fold increase in biological activity, and that will be great. So this is what the opportunity we have, and we need to exploit that opportunity for further drug designing. That's why it always says that research doesn't stop. Though you will have highest binding affinity for any molecule, we don't stop there. We keep exploring more opportunities for further designing, and that's why it is called as research. It is not just a search which was happened before. We do it repeatedly. That's why we call it as a research. So because those extended binding pockets are there, here you can see the ligand which is fitted inside, and in surface view even you can see this binding pocket is being extended. And specifically the things which I would like to focus here is, you can see these various blue or red color patches which are present here. So these patches says something, and what is that something? It says this particular for example, this red color is for hydrogen bond acceptor and blue color is for hydrogen bond donor. So these patches means this hydrogen bond acceptor, donor or hydrophobic patches are present there, means those properties are present inside the binding pocket, and we need to explore those possibilities. So for example, you can see here your ligand is particularly binding in this particular space, but still there are many hydrogen bond acceptors or hydrogen bond donors group are present inside the protein structure in various sub pockets. And let's explore those pockets and try to exploit that opportunity for further drug designing. This is what these extended pockets give you, that opportunity. So we need to analyze it carefully, and we need to see, can I explore this opportunity or not? So if the answer is yes, then definitely you should go for further drug designing, and you will get the better binding and ultimately a better biological activity value. So other thing which we would like to focus on with respect to binding pockets is, so there are various type of binding pockets. So basically here you can see these three images from three different protein structures, but you will be surprised to know these all, though these are three protein structure, but those three protein structures belongs to the same protein, which is human aldose reductase. So whenever we have multiple entries in protein data bank for a same protein, let's say example is human aldose reductase protein. So for that there are many structures reported, and I particularly pick, let's say, these three structures which has PDB ID mentioned here, like 1US0 and 1IEI 1AH3. So when I tried to explore the binding pockets of three protein structures which are solved by three different groups with three different ligands which are present inside it. For example, at bottom you can see the name of this particular inhibitor which is present there in each protein structure, and you can see. So what here we need to focus is on, we need to focus on the shape and size of binding pocket. And you can see in this particular structure on left hand side image, you can see the binding pocket is straight enough where the ligand is perfectly fitted inside this straight binding pocket, which you can say it is a straight or a linear type of binding pocket, where the inhibitor molecule which has ID IDD594, which was designed by some research group, and they got the biological activity of this particular inhibitor molecule in nanomolar range, which ranges from 3 to 30 nanomolar. So 3 to 30 nanomolar biological activity is also a great biological activity. So whenever ligand fits inside this particular binding pocket in this fashion, it gives you a better binding. But another research group worked on the same protein called human aldose reductase, and they solved the different crystal structure with different inhibitor which is called as zinarestat, and they got a different biological activity for other inhibitor which is 8 to 44 nanomolar. This is also great, but here this ligand is fitted inside the binding pocket in different way. I could say it is a C-shaped binding pocket, and in this way, like, different inhibitor acquired the different position inside the binding pocket of protein. So you can see here still that linear region is there, but additional pocket is being explored by the ligand, and it acquired somehow this C shape. When another research group work on the same protein and they crystallize the protein structure with another ligand called tolrestat, they got some binding pocket of some X-shaped binding pocket, and the because the molecule was might be in X shape, and then that molecule particularly fitted inside this particular binding pocket in this particular fashion. So you can see now, though there is a complete linear structure, but there are some gaps in between. Means ligand was fitted inside it, but it did not explore many various pockets, but still it is fitted inside it. Unfortunately, I did not get the biological activity of this particular molecule, how much it is, but for previous two molecules, there was biological activity reported. So you might ask question from where I got this biological activity. So the simple thing is you need to look into literature to see what is the biological activity of it, or if you, let's say, if you don't want to read many papers for it, then you can simply go to the protein data bank, and there you can find that for this particular molecule or the ligand molecule which is present inside it, what is name of that ligand molecule, and then what is the biological activity of this particular ligand molecule. And you can see here there are various biological activities are reported for this particular molecule which they got from different experiments. So that's one of the easiest way to get the biological activity value for any type of protein structure if it is reported in protein data bank. So okay, so the take home message is, though the protein structure is same, means a single protein can have different structures reported in protein data bank with different inhibitors with different biological activities, and they might have different shapes of binding pocket. So whenever you have this information available with you, what you will do with that information? You will try to see which protein structure I should proceed further. So it is always suggested that if you want to proceed further with like any of the structure, it is always better to choose a protein structure which has highest binding affinity inhibitor bound inside that structure. So for example, this particular molecule IDD594 has highest biological activity of 3 nanomolar as compared to others, and it is fitted inside it. So I would use this particular protein structure for further computer aided drug designing or virtual screening studies. So that could be the answer for 8. Means you need to analyze all those structures which are available in the protein data bank, and you need to do this comparative analysis and see which is the protein structure is of your interest and which protein structure you should go further with. So another aspect of exploring binding pocket is the same protein structure can have multiple pockets. So for example, here I am showing you the example of human serum albumin protein. So it is very well known protein which is called as human serum albumin, and it is responsible for binding of most of the excipients. So whenever we administered the drug and it goes to the serum, uh, there you will find this particular protein, and where the drug molecule first binds to this protein and then it gets transported. So because there are many such molecules, those molecules can have different shapes, different size, and they should bind to this particular protein. So because of that because it is a necessity for this particular protein to accommodate many different kind of ligand with different shapes, different size, different volume. So this particular protein can have various binding pockets in various shapes. So whatever you can see in the gray surface is the surface of protein, and various colored regions which are present are different binding pockets, so which are available for many different ligands, ranging from small size to big size, and they are available for the binding of different type of diverse ligands. So you can see here the take home message is, even there is a single protein structure present for a protein, any protein, you can have multiple binding pockets. So like it can have 10 or 20 different type of binding pockets which are present on the surface of protein or inside the protein. But the question comes afterwards, like which one is the best binding pocket for your molecule, that we can explore further, or that we need to explore further by using molecular docking technique or in-depth analysis of each and every binding pocket. So this is what all we need to do. Once you will get the scenario of in a single protein structure you can have multiple binding pockets, so let's explore it in detail and see which one is the best binding pocket. So the take home message is pretty clear: single structure can have multiple binding pockets. So whenever you get multiple binding pockets or a structure, because it needs to bind to various ligands. So story doesn't stop here. Whenever I say ligand, it doesn't mean that it confined only to the small molecule, but there can be many example where you will have protein type of interaction, means one protein binds to the another protein. So in that case, for example, here it is an example of one of the protein called cytochrome P450 BM3, and it can have various binding pockets which are categorized into deep binding pocket and shallow binding pocket. So whenever we say deep binding pocket, means those are small confined region which are present inside the binding pocket, and those are specifically responsible for ligand binding, and ligand means small molecule. So wherever there are small molecules present inside it, with you, like it can bind to the deep binding pocket which is predicted for this particular protein. But in case if there is a condition like you need to explore other binding pocket which is responsible for binding to a big structure, for example protein or DNA. So those type of binding pockets are mostly present on the surface of protein, and we categorize those binding pockets as a shallow binding pocket. So wherever you find such a big binding pocket on surface and those are shallow enough, those are mostly responsible for binding to the big protein structures. So this all information you can get it from the by visualizing this particular protein structure in surface view or analyzing it using the software or sitemap tool. So let's see it in a further. You can see the same protein structure which I said, it is an example of cytochrome P450 BM3 structure, which has this red color deep binding pocket which is responsible for ligand binding, means small molecule binding, and this magenta color patch is present on the surface of cytochrome P450 protein, and it is categorized as a shallow binding pocket, and as I say, it is responsible for binding to big biomolecules like another protein. So in this structure there is another protein called FMN domain of cytochrome P450 reductase protein, and that protein specifically binds to this big magenta color patch, which we call it as a shallow binding pocket. So the final take home message is a protein can have different type of binding pockets, and those are not only responsible for binding to small molecules but also responsible for binding to the big biomolecules like proteins or DNAs or antigens or antibodies. So that also we need to explore it further. So as I explained before, that there can be many binding pockets, but what makes those binding pockets favorable for the ligand binding? So what are those properties? So those properties are like hydrophobic regions which are present inside the binding pocket, hydrogen bond acceptor region, hydrogen bond donor region. So whenever it all combines together, it forms that favorable environment. So in our software, you will get such a view that in just a single view, you will get all that information related to the binding pocket. So let's talk about this particular specific example where this ligand is particularly fitted inside the binding pocket of a protein structure. In this yellow color region is responsible for hydrophobic packing, which is present in ligand or and in receptor. Then there is a region which is highlighted here in red color. So basically those red color patches are responsible for hydrogen bond acceptor region inside the ligand molecule, and wherever you find these blue patches, those are responsible for hydrogen bond donor region present in the ligand molecule. Means you can easily get an idea about which type of functional group should be present there at this particular position. So wherever I find this blue color patch, means there should be a hydrogen bond donor region present inside my molecule. If it is not present there, then I can incorporate that particular functional group, which is hydrogen bond donor, to increase the binding of this particular ligand. So in this way, we need to analyze it critically by looking at the output of our software called sitemap, and by visualizing it or analyzing it critically, we can decide which functional group I should incorporate inside the molecule to get a better binding. So that is called as rational drug designing. Means afterwards, once you will have those sitemap results with you, you will not put any random substitution at any random position inside the molecule, but you will go with specifically the specific substitution at specific point. Just an analogy, we can say it as a simple thing, like whenever a key maker makes a key, so initially he hypothetically put a key inside lock, and then he get various marks on the key, and then he specifically optimize each and every mark to get a better fit of key, so that it opens the lock. The same thing we need to apply here. So always remember, whenever we go for computer aided drug designing, don't ever think of doing irrational things. Always think it rationally, and always put all substitution design of your molecule rationally based on whatever information is available with you from literature, by software, or by any means. So for that, as I said, we have a very friendly tool which is called as sitemap. So with Schrodinger, you can find all those tools available in the task button. We will see everything in our demo presentations afterwards. But with this particular option is available as a sitemap in other applications in Schrodinger suite. So you will have access to it. So how does it looks like? As I said, it is very much user friendly. So it's pretty straightforward panel. You just need to load your structure and all information is present by default, and you just need to click on run. So by default, it works very well, and it will give you all possible binding pockets based on all that available information and properties which are present in the protein structure. And here there is an additional option which is present for detect shallow binding sites. So as I explained, if you are working on, let's say, protein interaction type of research, then you can also use this option, and software will automatically detect some shallow binding pockets which are responsible for binding to big biomolecules. So this is what a pretty straightforward tool is. Basically, you don't need to tick anything, just open the panel and click on run. It will run and give you the output. So question comes like, though it is very much easy, but how does it works in the background? So for that, this is just a hypothetical view of how it works in background, but there is more complicated algorithm going on for the prediction of binding pockets. So basically, you can see here on left hand side there is a grid, and in that grid we put a protein structure. So you can see here this dark gray color region is for the protein structure, and as I said, it is not at all even. So there can be many pockets, sub pockets, or various skins present inside the protein structure, and we see that all those skins, but we need to proceed further. How to identify those skins? So for that, we put points, basically probe atoms inside those small pockets, and we try to put all those probe atoms inside this binding pocket, whatever are present in the complete protein structure, and we try to measure how many probe points, means we call it as a site point, how many site points can be accommodated inside the single pocket. So you can see here in this protein structure there are three small pockets are present. Out of this, this one is very small, which accommodates only 5 site points, and another accommodates 7 site points, and there is another one which is big enough to accommodate many site points. Then we check whether can we connect those site points or there is a gap in between. So if we are able to connect all those site points, means we can say this is a continuous binding pocket which is big enough to accommodate many site points. And to get those if there are many site points, means it is big enough as a volume, and this big binding pocket can also accommodate a big ligand molecule inside it. So this is what the hypothetically this algorithm works. But of course there are many other parameters which are present in this algorithm, which makes it very complicated and reliable. So whatever results you will get, those are more reliable, so you can rely on it. So as a output of these results, you will get all those site points. So here you can see the protein structure with those patches, means hydrogen bond acceptor donor patches in blue and red, you can see. And what site points I was talking about are shown in this white points, white dots. So basically these are the site points, and as there are many site points present inside the binding pocket, and you can connect all those binding site points, it means your binding pocket can be big enough. So in detail we can see like which patches are present, how big the binding pocket is, how many site points are being accommodated inside it. So this is what in background it works, and finally it gives you this particular view where in just single view you can see which properties are present and where I can perform various modifications in my ligand molecule to get a better binding. So that's the view of this particular sitemap results. So based on, so far we have seen all type of visual analysis stuff. So visually you can see everything, but so we call it as a qualitative way, but there should be a quantitative way to find out which one is better, or according to rank wise, how can I put, how can I rank different binding sites. So for that we have a very good scoring method which is called as site score and D score. So D score is nothing but the druggability score. So whether that by any particular binding pocket, whether it is druggable or not. So it is described by this D score number. So wherever you get number like more than 1, which can be 1.1, 1.2 or something. So if it is more than 1, then definitely this is a D score. This particular binding point, binding pocket is definitely a druggable site. But if its score is less than 1, like 0.8 or 0.9, so in that scenario you can consider that as a probable binding pocket and you can perform further virtual screening on it. But let's say if it has a D score value of less than 0.6 or less than 0.7 or less than that, then you can ignore those pockets, because those pockets are not at all that much druggable. So whenever I say druggable, means those binding pockets must have all those properties, hydrogen bond acceptor, donor or hydrophobic property features should be present inside it in proper manner. Then only we call it as a druggable site. If it is not present inside such binding pocket in probable manner, then then those sites are not at all druggable sites. So not druggable site means ligand cannot fit or stay inside it. So this is what we need to analyze it based on scores. You will get a qualitative way of analysis, you will get the quantitative way of analysis, and it is pretty straightforward. So there are various formulas involved in calculating these scores, like site score or druggability score and binding site volume. So based on this volume information, you can get idea how big ligand can fit inside it. Based on druggability score, you get how druggable it is, and combinedly it gives you the site score, which ultimately tells you whether you should go further with that site or not. So it also means the parameters which it consider is hydrophilic score or enclosure scores, or how many number of site points are there. So in general, whatever we discussed in past few slides, all those things are being considered inside this course to give you the better ranking, to take a good decision out of all those binding pockets. So now, up to this point, we have identified various binding pockets, but we need to tell software that yes, I want to go further with this site for the further virtual screening, or I can say the docking. For further docking, you need to specify, or you need to tell software that this is the binding pocket which I need to go further with. So how to proceed further with it? So for example, if you have a protein structure and the co-crystallized ligand is already present inside that crystal structure, then it makes your life easy. So you don't need to do anything, because from experimentalist itself you came to know about this is the particular binding pocket which you need to use it for the further molecular docking exercise. So defining that particular binding pocket for the software, we call that process is called as grid generation. So whenever you have ligand or co-crystallized ligand present inside the pocket, life become easy. So there is a particular panel called receptor grid generation. It is also pretty straightforward panel which can have multiple advanced options, but maybe you don't need to worry about all those advanced options. It is just you need to open that particular receptor grid generation panel, and that's it. You will have option here, pick to identify the ligand molecule which is present inside the protein. You just need to click on any atom. I'm saying any atom of the ligand, and it will automatically identify this particular ligand molecule as a grid center for the molecular docking, and that's it. You can see here there is a box which is present in this magenta color. This particular box, we call it as a grid. So once you pick that particular ligand as a grid center, software will automatically do everything. You don't need to do anything. You just need to click on run, and that's it. So you can see here, out of this big protein structure, there is a small magenta color box, which is which is present around the co-crystallized ligand, and we call this particular region as a grid, where we are going to perform molecular docking of many other ligands. So this is what the process of grid generation is called. But this process we follow whenever you have a ligand molecule present inside it, but there can be a condition when you don't have co-crystallized ligand present in it. So in such condition, there is a sitemap tool to help you out. So using sitemap tool, you can predict various binding pocket in this way, and here you will give it based on these properties, you and the site score or D score, you can select this particular binding pocket as a final binding pocket. And once you have selected, okay, this is what the binding pocket which I want to go further with, or I want to perform a grid generation around this binding pocket, again you just need to go to the grid generation panel. And here, so because ligand is not present inside it, but to help you out, to make your life easy, you will have the sitemap results. In sitemap results, you will have these white color site points. So what you need to do is you just need to tick on any site point, even a single site point. You just tick on it, will automatically select all site points inside that particular binding pocket, and it will generate the grid around this particular binding pocket. That's it. Means in just single click, it will identify the binding pocket, and you just need to click on run. That's the procedure for receptor grid generation which you need to do. And sitemap is the tool which makes your life very easy. If you are working on the protein target which has co-crystallized ligand, we even co-crystallized ligand is absent, in that case also sitemap will make your life easy. And you can use that all information for the not only for the receptor grid generation, but also for the further designing of ligand rationally, which is very important in computer aided drug designing. So that's what we need to think of. And here I am about to conclude the session on binding site identification and analysis. I would like to acknowledge my team who are located in Bangalore, and we are working round the clock to solve your all queries, to support you in all way for your research. So we are always there. Please feel free to contact us at any time. And I would say thank you very much for joining the presentation and listening it carefully. And finally, my email ID is mentioned here. In case of further queries, you can always contact me. And I would like to open the session for questions if you have. Thank you very much again.
Thank you for the presentation, Dr. Prajwal. We do have time for a few questions. As a reminder, if anyone has any question they would like to ask, you can do that by entering them into the chat section of the YouTube video, and we will get them added to the list. So I'll be reading out the questions as it is. The first question is, can we use sitemap tool to map out binding pockets over the entire solvent accessible surface area at once?
Yes, it's just a simple thing. You just need to open sitemap and run. So it will identify all possible pockets, small, big, all type of sub pockets, and it will give you the all that output. But based on that output, you need to conclude which one is the best binding pocket. But yes, it will give you all type of possible pockets.
Right. The second question is, as the proteins are dynamic in nature, what is the minimum time in which we can say that ligands get fixed in the protein?
Yeah, so first of all, there is no straightforward answer for it. Depends on case to case, depends on the flexibility of protein. But overall, if you perform few hundred nanoseconds, let's say 100 or 200 nanoseconds of simulation, MD simulation, then definitely it will give you the idea whether ligands successfully placed inside the binding pocket or it is unstable inside it. So you will get that idea in 100 or 200 nanoseconds of simulation.
Right. Moving on to the third question. Can you find inhibition constant if you have the binding affinity?
So if you have binding affinity, so see, there are two different things. Binding affinity means something is binding to the protein. That is called as binding affinity. And inhibition constant is something which inhibits the activity of that particular protein. So for example, if a protein is responsible for catalysis of some reaction, let's say hydrolysis reaction, so after binding any like inhibitor molecule to that protein, whether it inhibits that process or not, so that's the completely different aspect. And the binding to the particular protein is a different aspect, though those events are correlated with each other, but I'm not sure if there is a formula to compute such thing. But still, there you need to remember those are two different events.
Is there any specific range for perfect biological activity, and how do we decide that?
So, perfect biological activity, yes. For example, if you have a nanomolar range of activity, biological activity, that you can see it is pretty perfect. But again, there are few examples where you will have biological activity in picomolar range. So that is again better than nanomolar. So, and other than that, even there are few drug molecules which has a biological activity in micromolar range, for example anti-cancer molecules. So I mean there is no very perfect thing exists, depending on your target, depending on the pharmacological area you are working on, nanomolar range of activity is kind of better.
Okay. Suppose we have different ligands bound to the same protein. On what basis do we choose the PDB?
So the basis can be biological activity of those different ligands. So if you have a ligand with better biological activity, so you can always go with such protein structure. That can be pretty straightforward.
How to find the allosteric binding pocket?
Yes, so allosteric binding pocket is also one of the binding pocket which is not orthosteric binding pocket, but it is present somewhere else in the protein structure. So you will get that idea from sitemap that other than orthosteric site, if you will get a D score of 1 point something for other binding pocket, so you can see this is also a potential binding pocket, and that can be allosteric binding pocket. But again, that's the allosterism is the different mechanism which one need to explore it further. So just by doing molecular docking, one cannot say whether there are allosteric effect on the protein structure or not. So you need to check it through molecular dynamic simulation, probably longer scale molecular dynamic simulations, and then you need to find whether it really gives you allosteric effect or not. So the sitemap will give you that option or assistance.
Is binding affinity itself enough to conclude respective ligands biological activity with ADME properties?
Sorry, I did not get what it is
Um,
exactly.
Okay, I think maybe there is a problem with this question.
Okay.
I'll just move on to the second one, come back to this later. Um, a protein may have more than one chains. What will be the impact if we delete or don't delete one chain or the other on the results of docking?
Yeah, so that's good question actually. So the thing is, whenever you have multiple chains present in the protein structure, you need to think wisely. You need to see where the ligand binding site is present. So imagine you have ABC, three chains present for in the protein structure, and your ligand binding pocket is present somewhere inside the chain A. So you will use that binding pocket for further virtual screening or molecular docking exercise. So in that case, because it's a rigid structure which you are going to use, by deleting other chains will not affect on your results. So that's one case. But in another case, for example, if your binding pocket lies at the interface of two chains, for example, interface of chain A and chain B, in that case, if you have such a binding pocket, then you need to retain both chains in your studies. There, if you remove other chains like chain B, then it will it will not give you the reliable results out of it, because for particular activity the togetherness of both chain is required. That is what biologically proven. That's why binding pocket is present at the interface of two chains. So in that case you need to retain it. So this is what you need to think wisely. You need to check the available aspects, and based on that you need to take decision whether should I keep all chains or whether should I delete other chains.
Right. The next question is, how do we select the best binding pocket?
So the straightforward answer can be based on the D score. So if you have D score value more than 1, then definitely you need to choose this as a best binding pocket. But as I said, if the score is less than, let's say, 0.8 or 0.9, then you can think of going further with such binding pockets. But if it is less than that, then there is no point in exploring it further. So D score can be a better parameter to choose best binding pocket.
Is it compulsory to see the Lipinski's rule of 5 for every molecule? What happens if they fail?
Yeah, so it's not at all compulsory. Even in drug bank, there are many drug molecules which are exceptions to Lipinski rule of five. So as such, Lipinski rule of five is kind of outdated now. But it can be one of the filter just to get an idea about druggable molecule. But that is not at all very. I would not consider it as a very reliable filter if you are working on some big molecules or natural product type of compounds. Then Lipinski is not the filter. So if you are working on small molecules, then yes, you can use it as a filter, but still I would not prefer to use Lipinski as a filter.
Right. Moving to the next question. So since we prepare a protein by protein preparation wizard, will it affect the binding site prediction?
So not really, because first of all, protein preparation is a essential step. So you must or you should go with protein preparation wizard before doing any exercise on the protein structure. So that's the must do step. So after protein preparation wizard only you can compute everything else. So before protein preparation wizard, because there is no completeness of structure, there are no hydrogen present in it, so we don't call it as even protein structure. So that's why like protein preparation is the must thing, and after that whatever you get is the reliable thing.
Right. The next question is, what differentiates the binding pockets from the rest of the protein surface?
Yeah, what differentiates? So the answer is straight, like the properties, binding properties, for example, hydrogen bond donor property, acceptor property, hydrophobicness, which all combines together and it makes that particular pocket as a binding pocket. If such things are present inside any pocket, that can be a binding pocket. If these things are not present proportionally in any pocket, we call it as a simple surface and it will not be a binding pocket. So that makes difference.
Right. Is there a way to find protein-protein interactions?
Yes. So for that, we have a tool called protein-protein docking. So you will have chance to explore that tool in separate session. But the answer is yes, we have tool to explore protein-protein interactions.
Why is it necessary to remove the water molecules from the protein structure when we see it in thymol? Or is
So
it necessary?
I mean, it all depends on you. You are the researcher. You need to think wisely whether this water molecule is important or not, whether it is conserved or not, whether this particular water molecule has biological role or not, whether this molecule is responsible for structural integrity of protein or not. If so these all things are basically mentioned in the paper for this particular crystal structure. So whenever you look any crystal structure in protein data bank, always it is suggested that you must go and read that particular paper. So all that information is present inside that paper, so you should read it, and then only you need to decide whether to keep that water molecule or not, or delete that water molecule. So it's all up to the condition.
If there is a binding pocket at the juncture of two chains of a protein, whether we need to take both chains for docking analysis.
Yes.
Okay, how to identify which protein-protein interaction is the good one?
So how to identify? It is based on uh, first of all, you can have idea about how those two proteins interact. Then other criteria can be you can see like which type of interactions are present there. Then next criteria can be a binding free energy between two proteins. So if it is favorable enough, then yes, you can see it as a good protein-protein interaction. But if that binding free energy criteria is not satisfied, like it has no favorable binding energy, then you can say it is a bad interactions. Another criteria can be after running MD simulation, you can see whether it remains stable, those interaction remain stable, that protein remains stably interacting with the one of the protein. If it is so, then you can see it as a stable interaction. If it is not stable, then you can say it is unstable. So there can be many criteria.
Right. Is it possible to perform pocket analysis on MD trajectory?
Yes, answer is yes again. So we have a simple script to perform the same binding pocket analysis for the complete MD simulation trajectory, and you will get answer for each and every frame. You will have the data of the binding site volume, binding site properties. Everything is present with you after running the simple script. So answer is yes.
Right. What is the threshold value for site score and D score? Is it possible to get the composite D score?
So threshold value is, as I explained, like threshold can be 1 point something, and above that is a binding pocket. Below that means you can ignore those binding pockets also, but it's all up to you. And the next part of question is composite D score. I did not understand what does it mean.
Right. I think we can just move on to the next question. Anybody who think that we haven't answered your question in its entirety, you can always email us. The next question is, okay, is there any specific distances in angstrom where we can predict type of bonding in between ligand and specific amino residues?
Yes, so for each type of non-covalent interaction, there is a specific criteria. So just take an example of hydrogen bonding interaction. So whenever there is a distance between hydrogen bond acceptor and donor atom is up to 2.5 angstrom or up to 3.5 angstrom, then it forms the hydrogen bonding interaction. It's not only depending on distance, but there should be an angle between three atoms. So whenever it satisfies that criteria, then only it forms particular type of non-covalent interaction. So that all information you can find it simply on Google search. So criteria should be there.
Okay, moving on. What is meant by a co-crystallized ligand?
So co-crystallized ligand means simply whenever experimentalist does crystallization experiment, and he does it with protein and a inhibitor molecule, and he tries to crystallize that particular complex structure, protein ligand complex structure. So if he is able to crystallize it, then you will get the protein structure and ligand fitted inside the binding pocket. That ligand we consider it as a co-crystallized ligand, means it is coming from the crystallography experiment. That's the experimental thing.
Right. The next question is, if you have a docked molecule with the best, I think it means docking score, and all the properties are fine according to the computational methods, can we take them into in vitro and in vivo analysis?
Yes, if you are confident enough on the property values which you are getting for all computational studies, then yes, that's the rationale behind it. You can put it for the in vitro studies and further in vivo studies.
Okay. We have a lot of questions.
Okay.
Right. Okay. How can we validate the active site predicted using the sitemap results?
Yeah, that's a good question. Validation should always be there. So imagine like you need to run a control calculation on the protein of your interest. So for example, you have a co-crystallized ligand present inside the protein. So the control calculation can be just remove that co-crystallized ligand from the protein structure and run the sitemap calculations. So after doing sitemap calculations, if you get the same binding pocket where previously co-crystallized ligand was present inside it, and that will be your top rank binding pocket, means it validates the sitemap results. And to my knowledge, so far whatever proteins I have worked on, sitemap gives you the best result. It always predict the same binding pocket where co-crystallized ligand was present. So that's the control calculation you can do.
The next question is, can there be more than one ligand in a binding pocket?
Yes, it's perfectly possible. So there are many such proteins like cytochrome 3A4 protein, or there can be many kinases where there are two ligands present in it. For be ATP, and another can be a inhibitor, or one ligand can be NADP and another can be inhibitor. So there can be multiple ligands present inside the binding pocket. Not only ligand, but there can be also ions present inside it. There can be water present inside it. So it's perfectly feasible.
For an apoenzyme where there are no active sites are present and no co-crystallized ligand, is it possible to get an active site predicted using sitemap?
Yes, so for sitemap, you can run it on any protein. It will give you an initial idea about where can be a possible binding pocket.
Okay, if there is a cofactor in the pocket, will that be a problem?
It depends. It depends on your research statement. So, for example, if you just imagine there is a kinase protein in which cofactor is present, let's say ATP cofactor is present, and you want to design a molecule which is a competitive inhibitor of ATP cofactor, then in that case you need to remove that ATP for the further exercise, even sitemap exercise. But if you want to design a non-competitive inhibitor which is not basically replacing ATP, cofactor, but it should bind somewhere else inside that same protein structure. In that case, you need to keep ATP for further screening, because that ATP binding site is not the one which you are targeting. You are targeting something else. So being ATP there is not an issue. But if you are designing a competitive inhibitor to that particular ATP, then you need to remove it.
Okay, the next question is, should we always go by the D score? What happens if the D score is lesser than 1, for example, 0.6? Can we also take their site and evaluate it further?
Yeah, so as such, if it is like 0.6 or less than that, you can simply ignore that site, because it has not many druggability features present in it. But as I said, you are the researcher who takes decision. So you can take that decision and you can proceed further with such a binding pocket which has a D score of zero point 0.6. And if it proves your hypothesis, then that's well and good. If it doesn't prove your hypothesis, then you need to go back to first step and think in another way. It's all up to you. It's a researcher's decision.
Okay, I think there are a couple of questions about protein-protein interaction. I'm guessing there's another session for that. Yeah, so we can answer all that in that session. Please make sure that you attend that one if you're interested. The next question is, can we use metabolites for docking?
Yes, so metabolites are also considered as a small molecule, and it's perfectly fine to use those metabolites for docking.
Right. I think there are way too many questions to go over them, to go over all of them. So I just wanted to make a quick announcement here that we do have an office hour today at 4:30 to 5:30. You should have received an email on how to join it. It's a Zoom meeting link with a password. So if anything gets missed here that we are not able to answer, you can join us there today in the evening, and we will be able to answer all the remaining questions. And obviously you can also email us if you want to email Dr. Prajwal. His email is right here, prajwal@schrodinger.com. I think we can take up maybe one or two more questions for now. Okay, apart from D score, any other parameter? Okay. Like some of the questions, like you should really write it as a question form, because it's very hard for me to just keep reading them and trying to understand what the question is here. Okay, is there any updated filter there for natural products when the Lipinski rule is outdated? Is there any other sort of a rule?
So, I mean, whenever you are working on natural product, it's already strange molecules which we are dealing with. So, I would say the filter can be molecular weight or number of hydrogen bond acceptors or donor. I could guess those filters might work based on your particular research statement, but there is no such specific filter available. You need to think wisely.
Right. Is it possible to calculate IC50 values in Schrodinger?
So, so let's not say it is calculation, but it's a prediction. So if you can build a QSAR model for prediction of IC50 values, then yes, you can do it with the Schrodinger software. but there is no ready-to-use tool to predict the IC50 value of any compound, and that is not at all available anywhere in the world. So you always need to go through QSAR method to predict it.
Right. I think we are almost at time for the next presentation. So as I told before, all of you, I'm sure I missed some of the questions. Please write to us, or you can join us at 4:30 today. So we'll move on to the second presentation of the day, theory, principles, methods of molecular docking by Dr. Pritesh. Dr. Pritesh, are you there?
Yeah,
Yes.
thank you very much. Let me just stop the sharing. And yes, so thank you very much, all of you, for joining the session. And I hope most of the questions are being addressed. If not, you can always write me, as Shelvia suggested. And over to you, Dr. Pritesh. Thank you very much again.
Thanks, Prajwal. Do you see my screen?
Yes.
Okay. Is my voice clear?
It is clear.
Great. Thank you. Thanks all for the patience. We are going through the wonderful lectures, very simplified way. The presentations are going on. Thanks to all the scientists here, my colleagues, Vinod, Prajwal. Yes, right. Thanks, Shelvia, for coordinating, taking up so many questions, and especially thanks to JSS and Manipal faculty who are panelists who are coordinating the questions and getting it from YouTube channel and putting it in the Zoom panel here. And a special thanks to Kaushik, who is individually monitoring all the questions. Right. Okay. We'll continue our discussion. The next technique, in fact, we would be discussing would be molecular docking. Okay. So we started our discussion with the drug discovery. So objective is to identify a molecule which can be used for treating a disease. So we started with our discussion. We understood what is the root cause for the disease. So we understood that it is the protein, and for treating the disease, okay, the overactivity of the protein we have to stop. That means the conformational changes happening in the protein we have to stop, whether it is a receptor, whether it is an enzyme. So we have to lock the protein in particular conformation. So if it is enzyme, you just prevent the conformational changes happening. In case of a receptor, you have to lock it in the required conformation so that the expected downstream signaling, you would be able to force it further. Okay, if you are working on an activator design, you have to lock the protein in the activated state, in the activated shape, right? And if you want a inhibitor to be designed for the receptor, then you have to lock the protein in the inhibited or inactive shape of the protein, right? Okay, so again, I'm sharing the same slide earlier we saw. So for computational drug discovery approaches, we have two approaches: structure-based drug discovery and ligand-based drug discovery. And our current focus area is structure-based drug discovery, where we are using structural information of the target to design the new molecule. So we started a discussion on what basis we choose these methodology, whether we should follow structure-based drug discovery or whether we have to go for ligand-based drug discovery. That is wholly dependent on what type of data is available about our target. If we do not have anything, we have to start from scratch. You have to literally go to the lab, synthesize some molecule based on your own intuition, come up with the data, and then you use the data. If there is a lot of information available on the ligand, but target structure is not there, then we go with the ligand-based drug discovery. We will be covering various tools of ligand-based drug discovery in a separate set of presentation. And then if the crystal structure is available, then we will go with the structure-based drug discovery. So when we started our discussion, we discussed on different aspects. So how to select the protein, how to select the ligand, all those aspects we discussed, right? So yesterday we had a nice session on how to select the protein, then how to prepare the protein, Then Dr. Vinod actually explained all these aspects on how to select the protein. Then Dr. Prajwal explained on various sources for the ligand. And yesterday we had a nice discussion on how to optimize these molecules. So if once you get those molecules, how you should process it, right? Okay. So for the drug design, as in the first session, Prajwal said, the molecule, we are trying to identify a key, right? The protein is like lock, and we are trying to identify a better key here, right? So if a molecule has to bind to the protein, so since we are going with the structure based drug discovery method, that means we are using the structural information. So binding site information we are making use here. So in the morning session, Dr. Prajwal explained how the site map will identify the binding site, and it would analyze, and it would give all the different types of information. It could be qualitative information, and it also shares the quantitative information. In the qualitative information, it would tell you, and it would analyze the binding pocket environment. So where are the hydrophobic region, where is or polar regions like acceptor or donor regions, right? All those type of analysis will do. Now, if a ligand has to bind to the protein, there are two things very essential. Okay, let us imagine this is the protein and this is the substrate or an inhibitor. If this molecule has to bind to the protein, there are two things very essential. The first thing is geometric complementarity. The molecule should be perfectly fitting very well with shape. The shape should be complementing perfectly. Not only that, the charge complementarity or electrostatic complementarity is also very important. So talking about the shape, let us imagine if this is round or elliptical in nature, still this substrate would have come and got attached itself to the protein, but there would have been gaps, right? So if there is gap, now inside the body, everywhere water is there. So water would get inside this pocket, the empty space, and it would push away the ligand. So tight binding will not be effective. There would be loose binding. Okay. And further, what is meant by charge complementarity or electrostatic complementarity? If protein has kind of donor, okay, if protein has donors charges, then the ligand should be having acceptor charges. So where from the donor or negative charge, positive charge is coming from? Protein is made up of amino acid residues, right? So amino acid residues will have different charged residues are there. The nature of residues are different. Excuse me. There are positively charged residues, there are negatively charged residues, there are hydrophobic residues, right? So if the protein offers like positive charged residue, then the ligand should be having the negative charged residue. So charge complementarity is also very essential if a molecule has to bind. I'll show you a small picture here. See how the molecule is going and binding. Okay. So now don't get confused between this picture and earlier picture what Dr. Prajwal showed. Dr. Prajwal showed when the ligand goes and gets attached itself to the protein, it is exploring all the binding site. Okay. There his orientation of discussion was to say where is the binding pocket and how the ligand would go and get attached itself there. So how it explores different pockets and finds the most comfortable place. Now here I am talking about, now we are taking a medicine, right? So yesterday we discussed about preparing the molecules. So ligand preparation we discussed about. So with ligand preparation, I get the molecule in the lowest energy conformation. So either we take the medicine in the form of tablets or injection or syrup, where the medicine is in the lowest energy conformation. So once it goes inside the body, then it is all surrounded by water, because everywhere in the body water is there. So again, in the water, we discussed about force field, the minimum energy conformation. I said environment effect will be there. So in the gaseous form, the molecule might be having one shape. Then in presence of water, it will have a totally different shape. The local environmental effect will be there. And even in the presence of protein, it might take different shape. That is what I'm bringing into your notice here. So you can see in the water, right? It is in the body now, it is inside the cell. See, the ligand is having different shape. Then once it attaches itself to the protein, it is adjusting its shape so that it can comfortably go and bind to the protein. Okay, this is the process of binding. So we use a term molecular docking. right? So to find out how the molecule goes and binds to the protein, we use this tool, molecular docking. Docking means a simple, if you see the simple English meaning of our docking, it is you are trying to place a molecule in particular place. Okay, so here we are discussing about molecular docking. It is not just the docking. We are not just placing the molecule, but in the biological system, how the drug molecule or a chemical molecule would go and get attached itself to the protein. That is what we are discussing. So there are two things we are trying to find out here. So as I showed in this picture, so first thing we are finding out is how the what is the shape the ligand will take when it is going and binding to the protein. So the first objective is finding out the binding mode. Okay, so let me make it further simple. Like, let's say I have a cyclohexane. So cyclohexane would be always in the chair form because that is the lowest energy conformation. If I synthesize and keep it in a beaker, cyclohexane is in liquid form, so always it would take chair form. If I make a medicine of it, cyclohexane, or cyclohexane is poison. Okay, let us imagine cyclohexane syrup I am making. When this cyclohexane goes and binds to the protein, with what shape the cyclohexane would go and bind? Would it bind in the same chair conformation or would it change? That is what we are trying to find out when I say binding mode. Okay, and the second thing is binding affinity. With what strength the ligand is going and binding to the protein, that is binding affinity. So you can define molecular docking as a computational prediction. It is a prediction. We are generating computational model here. So it is a computational prediction of binding mode and binding affinity between protein and ligand. So what is the application? So where all you can use this? You can identify mode of action, the binding mode you can predict. You can go for virtual screening. So you can collect all the database molecule like phytochemical collection or Asinex database or zinc database you can collect, and from there you can try to identify which is that molecule which can best attach or it can bind to the protein. Or you can go for lead optimization. Once you identify the hit, you can try to find out what type of chemistry modification if I make that would result in improvement in the binding interaction, and with that the potency, binding affinity will increase. So these are the few applications for the molecular docking. Okay, so again, brushing up our information, protein is made up of all the different amino acid residues, right? So tertiary structure of the protein is very essential for eliciting biological activity. So in the protein, in the tertiary structure, there would be binding pocket. So how to identify that binding pocket we just now discussed. So in the binding pocket, the ligand would go and bind. So it will form non-bonded interactions. Okay, there is no covalent bond formation. So hydrogen bond, hydrophobic interaction, these type of non-bonded interactions it would form. The drug will form with the amino acid residues in the protein. The ligand which offers more number of interactions, you can see the binding affinity will increase. With the increased number of interaction, the binding affinity will increase. See, this has only 2 hydrogen bonds. So -10 is the binding affinity. Then you see the third hydrogen bond came, the binding affinity increased. So the molecule which offers more number of interaction would be able to tightly bind with the protein. And in drug discovery, our objective is to identify that molecule which can tightly bind with the receptor. Okay, so what are the things required? So already we were going through different discussions. So we started, so we need to have the protein first, right? So how to select the protein? My colleague Vinod explained you other day nicely. So what all the factors you should keep in mind when you are selecting the protein, right? So whether it is inhibitor bound state or X-ray structure, so various parameters he explained. Okay, so once you select the protein, you have to process that with protein preparation wizard. So all the parameters will be there, right? Then once you identify the protein, in that where is the binding site you should be knowing, so that site you can explore. So how to identify the binding site, we had a nice session today morning. Then you need to have the ligand. So you have to take the ligand and you have to dock it, right? So what is the source for the ligand? So if you want to consider any database, we had a nice discussion by Dr. Prajwal who gave you information on the various databases. Or you want to design your own molecule. So various approaches like reaction-based enumeration or library enumeration, all those tools we discussed yesterday. So once you have the ligand, you have to process it. So we discussed about ligprep, how to process the molecule. So these are the requirement to start with our process, and how to collect, how to process, all those things we discussed. Next, we have to go for docking, and how to set the docking parameter, how to run it, all those things we will be discussing now. Okay, so already we have discussed about protein preparation wizard, so I'll not go into the details. So we have a nice tool where any lacunae present with the protein, like missing hydrogens, missing side chain, proper ionization state generation, extra chains if it is there, or extra water if it is there, all those things you are trying to remove it. Okay, so then we also discussed about ligand preparation, ligprep module, where you are optimizing the ligand. You take care of geometry, you take care of ionization state, you take care of stereoisomers, all those things you are taking care. The next thing is binding site identification. So for binding site identification, I can use, if you are picking a protein which is already bound with the ligand, then there is a high chance, okay, there is more than 90% chances that the newly designed molecule would go and bind to the same site. So I can use the same information. If suppose I don't have the ligand in the binding site, then I can go with the site map, just now we discussed, right? So we can identify the binding site. How does a docking program works? So let us try to understand here. Okay, any docking program you consider, it will have two components in it. The first one is called as search algorithm. You saw in the video, the ligand was changing its shape. So after I run the ligprep, we are running the ligand optimization, right? So when we run the ligand optimization, so yesterday when we discussed, so we are trying to reproduce the molecule the way it exists in the nature, because it has not yet entered the body. So when I start, I will be having molecule in the lowest energy conformation, but when it enters, it is in the water, it may adjust its shape. Then it would go inside the protein, and further it is adjusting its shape, and it is forming different types of interaction. So how to predict that shape changes happening? So to take care of that, in docking program, we will have the first program or first algorithm called a search algorithm. So it will generate the conformations. Okay, so it will rotate the dihedral angle here. Wherever there is single bond, it will change the dihedral angle and it will generate new shapes. Okay, if you change this dihedral angle, then you would be able to get molecule with a different shape. So each shape is called as conformer. So the plural form of this is conformers. Okay, so like this, the same ligand with the different shape we are getting. So latch together shapes we will generate for the single ligand. Okay, now each and every ligand it will take and it will put inside the pocket. Okay, because protein we are not considering flexible during docking. Protein we consider as a rigid. So one by one we will take each shape and then we will analyze. Now the second component of docking program comes into picture, that is scoring function. So this scoring function will calculate what is the binding affinity, with what strength the ligand is binding with the protein. Okay, so how does it calculate? It calculates the individual contribution coming from each type of interactions. So for example, energy of van der Waals interaction, energy of electrostatic interaction, energy of hydrogen bond, energy of hydrophobic interaction, pi cat interaction, pi stack, like that. So all the non-bonded interactions contribution, it will calculate. So from that, the ligand or the conformation which is offering maximum number of interaction, it will identify, and that would be shown as the best one. Okay, so when the ligand goes and binds to the protein, the complex should be stable. So that is what it is trying to find out here. So when it calculates the interaction energy, okay, so with which type of interaction both the protein and ligand is getting stabilized, that is what it is calculating. In Schrodinger, for docking, we have a module called as GLIDE. Okay, it is the short form is GLIDE. The full form is grid-based ligand docking with energetics. So we specify the binding pocket onto a grid, and then we take the ligand and we go for docking, and it calculates the binding affinity, the binding energetics it calculates. Okay, the unique advantage with Glide, with no other software offers, is you have a choice here. So you have a choice between speed and accuracy. So you want to go with the fastest mode, you start with HTVS, high throughput virtual screening mode. Okay, then the next precision mode is standard precision. Now HTVS or high throughput virtual screening mode will take about 1 second to dock the ligand. Standard precision will take about 10 seconds to dock a ligand, and extra precision mode will take about 120 seconds, 2 minutes. Okay, so what is the difference here? Any difference should be between these two programs. There is search algorithm and there is scoring function. So any difference in these three methodologies would be between that, right? So in case of HTVS, the number of confirmers or sampling generated by search algorithm will be in few thousands. So scoring function would quickly then finish the binding affinity calculation. So it is very fast. But since you are now generating only few samples, the accuracy may not be there because you are not exploring whole of the conformational sampling. So larger dihedral angle deviations you are taking. So in case of standard precision, the conformational sampling is increased. Okay, so here it will generate lax together conformers. So each conformer, it has to analyze what is the binding affinity by scoring function, right? So obviously it will take longer time. So that is why now, since the sampling is more, it is more accurate compared to HTVS method. Now, why extra precision is taking 120 seconds? Of course, the sampling is more. Okay, conformational sampling is more. Not only that, the scoring function is also further refined. We will discuss about how different is extra precision scoring compared to standard precision after some time. Okay, so as I mentioned, Glide is a grid-based method. So we map the property, binding site property onto a grid. So what is the shape of the pocket? What is the size of the pocket? What type of amino acid residues are there? What type of interaction they can offer? All those information we will map it onto a grid. Okay. Then while docking here for conformational analysis, we use core plus rotamer group approach. Okay, core means any bicyclic ring, any rigid rings are there. We use the predefined or pre-generated conformers because these are rigid. So few conformations only possible. So that we have pre-generated and we use that. Wherever there is rotatable bond, the single bond, we go for systematic search method. Conformational analysis will be carried out on the rotamer approach, rotameric bonds. So this is how the binding affinity is calculated. Okay, so the binding affinity score here is called as Glide score or docking score. So as I mentioned earlier, it is calculated by checking the individual contribution coming from each type of interaction, like Coulombic interaction, von Roel's interaction, lipophilic interaction, hydrogen bond, etc., etc. So several type of individual interaction, the individual contribution coming from each type of interaction, it will calculate. Okay, so this is how the output of docking result appears on the table. So this is called as extra precision visualizer. Okay, so here you would be able to see the binding affinity. So higher negative number indicates higher binding affinity. So larger the number in the negative side indicates higher binding affinity. So minus 11 is more potent than minus 5. Okay, the kilocalorie per mole is units of measurement. So here you would be able to see all the individual interactions, what is their contribution. So you can see in the violet color. Okay, and these are all hyperlinks. So you can see here kind of box like thing. These are hyperlinks. The moment you click on this box in the visualizer, so when we take the demo, you would be able to appreciate it. So when you click on this, it would show you, it would highlight you all those interactions. For example, hydrophobic interaction, which all the amino acid residues are offering hydrophobic interaction, which are the residues offering hydrogen bond. So like that, all those interactions you would be able to analyze. Now the uniqueness of Glide extra precision docking is it not only calculates the contributing factor, it also calculates the problematic part, penalties. Okay, this is very unique with Glide. No other software will calculate the penalties. Okay, so let us go into the detail why extra precision is taking longer time. So I said sampling is more. So we were discussing about HTVS, which takes just 1 second, which is very fast. whereas standard precision takes about 10 seconds and extra precision is taking about 120 seconds, 2 minutes per ligand. So why it is taking longer time? Of course, the sampling conformational analysis is more. Not only that, the scoring function is further refined. So how it is different? So if you consider the hydrophobic interaction, it is actually hydrophobic gain, which is result of all the hydrophobic amino acid residue. And that is what we have implemented in extra precision mode of scoring. So generally all the software will calculate like paired atom interaction. So they will consider one atom from the ligand, one atom from the receptor based on the distance they calculate. So that is not the actual representation. But here we consider all the hydrophobic amino acid residue, totally how much they are offering the hydrophobic gain. That is what we are calculating. Hydrogen bonds. Now there are different types of hydrogen bond. It can differentiate even the minute to minute changes in that. So it could be between neutral moiety, it could be between charged neutral moiety, right? These are the things. Sometimes you will see very special type of interactions, polar and non-polar interactions coexisting, like here. Okay, you can see now polar interaction is one extreme end of scale and non-polar interaction is another extreme end of the scale, and you will see both these opposite type of interactions coexisting at one place. Both of them simultaneously will be there at the same place, and these are called as signature type of interaction. So no other software will recognize. Schrodinger glide recognizes very efficiently these type of interaction, and when you see these type of interaction, these type of ligands would show very good very strong binding affinity. Now this molecule, if it has to come out of the pocket, it not only has to bind the polar interaction, for example hydrogen bond, it also has to break the hydrophobic interaction. So simultaneously breaking multiple interaction is very difficult, because interactions will not give summation effect. 1 + 1 will not become 2, rather it becomes synergistic, right? 1 + 1 could become 3 or 4. So it results in a very strong binding affinity. Not only that, very weak type of interactions, so pi-cat, pi-stack interactions or halogen interactions, these are very efficiently identified extra precision mode of docking. So these, their individual contribution might be very less than 0.5 kilocalories, but when they coexist with other interaction, they influence, or they will have a synergistic effect, and you would observe like 10 times or 20 times improvement in the biological activity. That we have implemented very well. Okay, coming to the penalties. Now these penalties will help differentiating a false hit with a true hit. Okay, no other software will detect this. So penalties like burial penalty. So if there is a polar group, if it is buried in a hydrophobic pocket, it would put a penalty. Okay, then if there is solvent exposed hydrophobic region is there in the ligand. Okay, for example, here you can see the surface of the receptor, and this is a hydrophobic region of the ligand. It is exposed, it is coming out of the receptor. That means it is solvent exposed. So this is something like all oil you are putting in a glass of water, so it becomes unstable. Okay, that is why it is putting that penalty. Or if there is rotatable bonds. So what is the problem if rotatable bonds are there? Ligand will become very flexible, so it will not be rigid, so the binding tightness will reduce. Not only that, now since it has so many rotatable bonds, it can change its shape. So with this particular shape, it could come and bind to this particular protein. Not only this, now it can change the shape, because these are single bond. It can change to any shape, right? It would change the shape and it would go and bind to some other protein. Now in the disease condition, this particular protein is problematic. So I want to suppress the activity of this protein. But some other protein is working normally, right? And normal functioning is required. If this ligand changes its shape, it would be able to go and bind to that other normal working protein. If it blocks the other protein, okay, that would result in normal functioning and you get the side effect. So always remember, the side effect you observe for a molecule is mainly because of off-target effects. Okay, and then we also have something called as ionization state penalty, epic state penalty. So if unstable ionized form is shown with higher binding affinity, it would put a penalty term there. So Here is a comparison between different docking programs. So you can see the Glide is outperforming all the other tools. And during docking here, you can consider whether you want to go with metal, presence of metal it can take care, presence of water also it can take care. You want to apply any constraints, so any biasing you want to apply, that is also possible, like hydrogen bond constraint, position constraints, metal coordination constraint, core constraint, or torsional constraint. So all those flexibility you have here while running the calculations. So in docking, we have various variations. Okay, so already we discussed about HTVS, SP, and extra precision mode. So what is the advantage of having these type of choice between speed and accuracy? So yesterday somebody asked, so if I have a huge database, how can I go? So shall I put all the molecule or only few molecule I have to pick, or how to pick the molecule? Rather, here you can go, you can follow a smart approach. Let's say you have a very huge database. Now, if you go with all the database in an extra precision mode, it will take years together to finish. Let us say I have 10 crore molecule collection and I want to run the virtual screening. Extra precision will take at least 5 years to finish the document, right? So rather, first we will go with the HTVS method, high throughput virtual screening method. It's a very fast method. Okay, it don't take much time. Just 1 second it will finish. The search algorithm scoring function will finish the docking in just 1 second. Okay, so initially you screen whole of the database with the fastest method, but this method is not very accurate method. So whatever results you get, top 5% of the result you take and resubmit it to next precision level, standard precision. Okay, number of molecule you have reduced, but you are reconfirming it with the more accurate method. But I have one more best method, the extra precision mode, the best accuracy method. So whatever result I get from standard precision, take 5% of the results from standard precision and resubmit to extra precision mode, because this is the best mode to identify. Okay, now see, this is a smart way of working. I explored whole of the database very quickly. I did not omit out any molecule, but whatever molecule I finally selected, I tested it 3 times, and the most highest precision level also I used to confirm that. So that is the advantage you get only with Glide, because you have here choice between speed and accuracy. This type of calculations or this type of simulation you would be able to, this type of workflow you would be able to try. Further, we also have cross docking. So here in the previous method, HTVS or SP, we kept single protein and we took a collection of ligand. Okay, rather I want to do it in a different way. I want to consider multiple proteins, or there is a multiple binding site in the protein. I want to explore which of the binding site the ligand is binding. So you can specify multiple grid files, even multiple combination of ligands also you can specify. That is called as cross docking. Then induced fit docking, we will be discussing about this tomorrow. So in case of Glide, we did not consider flexibility of the protein. So if you see the program, so I told there are 2 components. There is search algorithm and scoring function. Okay, search algorithm will implement the conformational flexibility for the ligand. Okay, whereas scoring function will calculate the binding affinity between ligand and protein, but there is no component which considers the flexibility of the protein. So it is a rigid protein, flexible ligand docking protocol. But as you saw in the pictures, protein is not stagnant. Protein will also have flexibility. So if you want to consider the protein flexibility, then you can go with induced fit docking. This is a complete flexible docking where both the protein as well as ligand flexibility is taken care. Tomorrow we will be discussing about these details. You want to implement quantum polarized charge approximation. Let's say the binding site is covered with lot of polar residues. So force field will sometimes fail, not with OPLS3. So this was olden days, it was a problem, but now we have latest force field. So this is not problem, but still if you want to approximate the quantum mechanics charges, then you can go with QM polarized ligand docking. We also have option for peptide docking. So if you are designing peptidomimetics and all, so you can go with the peptide docking. Macrocyclic compounds. So what is meant by macrocyclic? The molecule with the ring system having more than 8 members in the ring, 8-member ring, 10-member ring, 12-member ring, right? So cyclic system with at least 10 members in the ring or 8 members in the ring. In such cases, normal conformational sampling will not be really efficient in exploring whole of the conformational space. So for such cases, we have a specialized sampling technique called as macrocyclic sampling that you can implement. Also, we have in Schrodinger covalent docking. So generally, people would not prefer to go for covalent binding because we want the ligand to bind for some time and then it should go out. It should not permanently damage the protein. Once it exhibits its activity, it should go out of the body. If you want to permanently damage the protein, like for example in cancer and all, so in such cases or in antibacterials design, right now in COVID research for Mpro protein, there are covalent inhibitors reported. So you want to permanently damage because you want to kill that organism, right? So in such cases, you can go with the covalent docking. So for that also, we have options. Okay. So with that, I'll stop here my presentation. Thanks for your patience. So yesterday, I already gave you the details how you can get the information on installing the software and getting the license on it. So please go through my yesterday's video if you have missed that. So you can register in our website to activate the account. So without activating the account in Schrodinger website, you will not be able to download the software. So you can visit this page, www.schrodinger.request account to have a account in Schrodinger. So once you get the account, you will get a password. You can download the installers. Okay, setup file you will be able to install. Then you would get the access. Further, if you don't have the required hardware configuration, we discussed also about the hardware configuration. So minimum hardware required is Core i5 processor, 4 GB RAM is needed, and 1 GB dedicated graphics card is needed. So whether it is laptop, whether it is desktop, whatever operating system is fine, Linux, Mac, or Windows, any operating system will work. But you should have at least Core i5 processor, okay, 4 GB RAM, and at least 1 GB graphics card is needed. So if you have minimum hardware requirement, you can download the software and install the software on your own machine. Okay, we will help you with the license. If you don't have the machine, then you can opt for a certificate course. So online certification, again, the pricing and all will be discussed soon. So we are working out, as I mentioned. So since we have to, we are taking cloud access. So the cloud service provider is charging us. So we are trying to work on it. And that cloud service providing charges only we are charging here. So this is a certificate course. So online cloud-based access, you will have different chapters here. So you would be able to go through the various course materials. So once you complete this course, you will get the certificate, and you also get a badge which you can put on your LinkedIn. It will be a value addition for you. And further, if you have any questions, you are free to write to me. If you want to reach out to me, you can write to me at my email ID. You have any queries regarding this course or certificate course or anything related to this webinar, you can write to ddcourse@schrodinger.com. Thank you. So if there is any questions, I'll be happy to take up.
Thank you for that presentation, Dr. Pritesh. We do have a couple of questions. So the first question is, what is the range of best glide score?
Okay. See, when I was presenting, I did not talk anything on the score. I said the first objective of docking is to identify the binding mode. Okay. Then the binding score comes. For the given binding mode, what is the score? That is how we are calculating. There is no standard number, or it is not an absolute value to say this much should be the number. Okay, so it depends on protein to protein. So you should have a standard molecule, and then based on that you can compare. Let us say I have a standard molecule whose docking score is like, whose activity is, let us say 10 nanomole IC50, enzyme inhibition constant for that molecule is about 10 nanomole. If the 10 nanomole compound is showing a docking score of -15, then what is the score you are getting for your molecule? That is one way of comparing. Okay. Or now this same molecule, if I put and dock it into some other protein, Okay, some other crystal structure, same receptor. Let us say I am working on EGFR. If I take two different crystal structure, in one crystal structure I get one docking score, minus 15 I got. Now the same ligand I'll dock it into second protein structure of EGFR. I am getting here the docking score of minus 10. Okay. Now for this particular structure, what is the number I should be expecting? That is how you should implement. So there is no hard and fast rule that this is the number to get. So for some protein structure, minus 5 could be a potent molecule, and for some structure minus 25 also could be a less active compound. You have to compare with the standard molecule, and that's how you should be able to compare the activity of the molecule.
Okay, moving on to the second question. What we have to do if a 3D structure of your protein of interest is not available?
You can go with homology modeling. That is one option which we will be discussing tomorrow or day after tomorrow. So using a template, you can try to generate a structural model for your model. That is one option. Or if there is plenty of ligands reported, then you can go with the ligand-based drug discovery method. So pharmacophore, QSAR, shape-based screening, a lot of methodologies are there in the ligand-based drug discovery method. Those approaches you can try out. We will be discussing all those details in the forthcoming discussions.
Right. I think the next question, there seemed to be some sort of a confusion. I saw that this even in yesterday's presentation. People think that LigPrep generates conformers, and they're asking if you're generating conformers in LigPrep, why does like docking algorithm also generates them and stuff like that?
Okay, let me clarify. Yesterday also we took the same question. LigPrep doesn't generate the conformation. Don't get confused if you are getting more number of molecule as output than the input molecule. Okay. LigPrep has options for generating tautomers. So if there is a keto-enol tautomeric form possible, let us say you have sketched a molecule in keto form. If the enol form can be formed, it will generate two output, one with keto form, one with enol form. So two output it got. Let's say the same molecule had an ionizable group. Okay, there is a carboxylate ion in that molecule. So at given pH, the pKa of molecule is such a way that the molecule the 50% of molecule is existing as ionized form, 50% is existing as unionized form. Let us imagine it will generate both the forms then. Okay, so already it had two keto and enol form. Now another two it has generated, that is one with ionized form of functional group in the molecule, that is acidic group. Okay, carboxylic acid, one in the ionized form, one in the ionized form. So total you got now 4 molecules. Let us imagine the same molecule had one chiral center. Okay, one chiral center. So it will generate all these 4 molecules with R conformer, and the same thing it would generate with S conformer. So another 4 molecules it will generate. So total 8 molecule you are now getting as output molecule. Okay, I hope you are understanding what I am talking about. So it doesn't generate the conformation. It is just generating different chiral isomer, or it is generating different tautomer, or if it is generating just different ionization state for the molecules. So please don't get confused. It would be different forms of molecule it is generating. It is not generating the same molecule, but it would be generating different molecules. Okay, conformation analysis is you are just changing the shape of the molecule. You are retaining the same structure. If the molecule is existing in the ionized form, for conformation generation, let's say you are generating 10,000 conformers, 10,000 shape. So all the 10,000 shapes generated will have same ionization state. It would be in the protonated form or a deprotonated form. If you are taking a R form of a ligand or S form of a ligand, during conformation generation, you are not changing the chiral isomer. It would remain same. But LigPrep doesn't generate the conformation. It will generate different forms if possible. Different structures it will generate for the ligand.
Thank you. The next question is, can we dock the protein with a ligand in such a way that it can be in active state and it prevents inhibitors from inhibiting that protein.
Okay, there are two things here. Okay, protein existing in activated state and protein existing in the inactive form. You can consider protein in the activated form. You can make a organic molecule bind to it so that you can block the protein. So most of the people will try this approach, because protein, if you target and inhibit in the activated form, okay, protein when the shape is in the activated form, you get better potency. Okay, also you can inhibit the protein in the inactive form. The protein shape is in the inactive form. You make any molecule, any organic molecule able to bind to this inactive form, you are locking the protein in the same shape, then you are inhibiting it in the inactive form. So this approach depends on what is your requirement. Now generally what happens, since everyone tries, or all the proteins generally people try with the activated state of protein, like for example kinases. So for all the kinases, ATP is the substrate, right? Then in the activated state, all the protein will have almost same type of shape. So getting selectivity becomes problem. So to avoid the off-target effect, to get the species selectivity or the isomer selectivity, then people will choose whether if I consider activated state would be better, or if I consider inactive form of the protein better. So with that, they will strategize. So it all depends on what is that you are looking for. Depending on your research interest, you have to choose what suits you best.
Right. The next question is, if I am working on a new target and I have no idea about any small molecules that binds to it, how do I start with that?
Okay, very good question. So if you don't have any information, at least if you have structure, something you can start from there. You run the sitemap to identify binding pocket. If it is not there, get the sequence information, generate a homology model, identify a suitable template, and generate a structural model for your target. Now you are having structure of the protein. So it may not be very accurate, but it is a structural model. So some starting point you are getting. So it is always better from nothing to start something you will have in your hand. So you can start the virtual screening and identify the best molecule. So these are the various approaches you can start. So if the ligand information is not at all there, so you mentioned it is totally a new target, nobody has reported till now ligand. That means you have to go with the structure based approach or de novo approach, virtual screening approach. You can take a database collection of molecule. On this generated homology model, you can go for docking and try do the biology activity, the best molecule which is showing stable binding with the model, homology model of the target structure. You can pick that, you can do the activity. So you can, since so initial few set of molecule you can take, do the biology activity. So you can check whether you are able to generate a correlation between observed biology activity, the wet lab activity, and the computational model. If it is falling in line, that means the generated model for computer is very good. If the correlation is not really good, then you already have here few information, you can try to improvise. So you can go with the flexible docking method, you can go with molecular dynamics, and you can try to further refine your computational model so that it shows better correlation and you get better quality results. So that is how you can follow different approaches when you don't have any information, much information on the target or the ligand.
Moving to the next question. If we found unfavorable interactions after docking, what does that mean?
Unfavorable interaction, generally see, if the protein ligand complex is stable, then only the ligand would stay with the protein for a longer time. Everything is energy game. Okay. So yesterday we were discussing about ligand. So why, in what form it will exist? It would be in the lowest energy conformation. So if ligand has to go and bind to the protein, if the complex energy is less than their individual energy, then only it will form a complex. Once again, if ligand has to bind to the protein. If the complex's energy is less than their individual separated energy, okay, when they are existing as separately, if the potential energy is less, they will never form the complex. If when they form complex, if the energy is becoming less, if it is becoming more stable, then only they will go and bind. Okay. Now with these bad interactions, if there is a perfect complementarity, if you remember, I showed you the shape complementarity and charge complementarity picture. So if this happens, then there would be a better complementarity, lot of interactions will be there, perfect fitness of the ligand with the protein will be there. So the ligand would tend to stay with protein for a longer time. If this is not happening, if there is a hydrophobic group which is exposed towards a polar functional group of the receptor pocket, now they don't like it. Like polar and non-polar interactions are, they don't like each other. So if you see something like that, ligand becomes restless. Ligand doesn't, it is kind of strained. What is meant by restless? Restless means it is some layman language I am telling you. Okay, ligand will have strain because it is not liking that environment. It want to come out. So that's how it destabilizes. So that is what we try to find out. So if there are bad interactions, so in Schrodinger glide docking, we have penalties. So the penalty terms would be able to efficiently recognize, okay, there is here, there is some bad buried interaction is there, some bad contradicting complementarity is there. There are a lot of rotatable bonds are there. The ionization state is a problematic part. It would immediately recognize, it will put a penalty. So the scoring pattern, scoring matrix is very well refined. So it would chop off, it would be able to handle all these problems, and it would be able to efficiently differentiate a true hit with a false hit.
Okay, thank you. Moving on. Does strong binding affinity and inhibition constant values signify good biological or therapeutic effects?
See, there are two things again here. What we are seeing in docking is the microenvironment, how the molecule goes and attaches to the protein. But to become a molecule drug, it is not just the potency which is sufficient. If molecule shows higher binding affinity, more number of interaction, potency increases, but that doesn't guarantee the molecule will have good ADME, right? So ADME component is a separate thing for which you have to do different type of studies. Okay, so just potency is not sufficient for a molecule to become drug. So that you should keep in mind. Just docking is not good enough to say the molecule is tightly binding and it can become drug. No, the molecule should have good potency as well as it should have good ADME profile. Then only a molecule becomes acceptable as a drug molecule.
Right. The next question. So you explained the various modes of glide, and you told like some of them generate a certain number of conformers and some of them generate more. Is there a way to set the number of conformers that can be generated for a ligand in while submitting the job for glide?
If you put a limitation, then you are restricting something. That is not good, right? So these are default methods. So we have fine-tuned the sampling. That is more than good. So anything you put the number, that means you are not allowing software to completely explore anything. So I wouldn't recommend that.
Okay. So the next question is, if there is a metal in the protein structure, but it does not have a role in binding, but it does help in maintaining the structural integrity of the protein, should we remove the metal ion or keep it for docking?
See, it all depends on your research requirement. If, see, in the docking, you are seeing only the microenvironment. What is important is binding site and around the 10 angstrom. That is what you are seeing, because non-bonded interaction will have influence. The far interactions influence would be up to 10 angstrom. Very weak influence will be there. Nearby, like within 4 angstrom or 5 angstrom, there would be very heavy influence will be there. Like non-bonded hydrogen bond, hydrophobic interaction, those all influence will be there. But up to 10 angstrom, they will have influence. Beyond that, anything is there, docking really doesn't see it. Okay. Per se, docking will not see. But if this metal, what you are talking, you are saying it is not in the binding site, but it is required for structural aspect, you are saying. If it is falling beyond 10 angstrom during docking, you keep it, you don't keep it, it doesn't really make any difference. But if you go for a different type of approach, let's say you want to run the molecular dynamics, in such cases you have to keep it, because the metal is influencing the structure of the protein. If you remove the metal, then during MD simulation, protein structure may get changed. So you have to understand each application's capability, and based on that you have to decide, so what suits best for us.
Right, thank you. So the next question is, I think you talked about that you can set certain constraints while performing docking. So the question is it not irrational? Aren't you introducing some kind of a bias while you are setting the constraints? And when should you actually be using the constraints?
You are absolutely right. If we are putting constraint, means we are biasing. So biasing is not advised. But if you have a very strong evidence based on your experimental results, based on your own, so let's say you are working on a particular research project for very long time, similar type of molecular handling, and very long time you have been observing. Okay, you will understand that particular scaffold would always occupy in the same way. So in such cases, if you have experience, if you are very sure about that, then you can apply those type of constraints. It is all knowledge based. As Dr. Prajwal suggested, this is a research. We have to find out whether I have to put the constraint, should I try without constraint? That is the research, right? So we have to try out various things and then find out which method really works better for us.
Thank you for the answer. The next question is, so I think it's a very general question, not just about docking. What happens if you're running something like a long virtual screening and some your software stops, your computer restarts, or electricity goes? So is it possible to resume the docking job later?
Yes, you can resume. You have command line options, you can do that.
Okay, so you can write to us if you need help with that. Also, if you go to our website, there are some knowledge-based articles which you can obviously get access to if you have a website account. So all these general issues will be addressed over there as well. Okay, so the next question is it possible to differentiate whether the bound ligand is agonist or antagonist?
See, computational methods will not tell you whether it is agonist or antagonist, but by seeing the receptor shape, you can say whether it is an activator or inhibitor. Per se, we are not looking into intrinsic activity. Now, this intrinsic activity brings out this positive activation or inactivation, right? So we don't calculate the intrinsic activity during computational studies. We calculate the binding affinity. Okay, but if you see the receptor, now receptor in case of GPCR will have activated state, so the conformation of protein will be totally different. You find out whether in the activated state of protein, particular ligand, if it is able to go and bind to the protein, and can it lock that protein in the same shape for a longer time, then that will behave as an activator. If the ligand is going and binding to the inhibited state, okay, if it is able to lock it in that particular shape, then it will behave as an inhibitor.
Right. The next question is about the grid box. So would you please discuss on the inner box or grid box, like when we should change the size of the inner box and when we should not, and how the result varies with the size of the grid box?
Okay, I did not go into the much details. I did not want to confuse you on the exact protocol what we use when we go for docking. Okay, so I wanted to keep the things very simple, so I just told it is search algorithm then the scoring function. But actually when you go into the docking, especially in Glide, there are various steps. Okay, so there would be initial generation of the pose, then refinement of the pose, minimization of the pose, then it will horizontally explore what is the space best suits for the ligand. Lot of things are there. Probably you can if you are very much interested in exploring and getting all the details, you can go into the manual. So once you install, you will get a help manual. So there you would be getting all the details. So inside the green box, the inner box, what you said, that is the place where spatially it will look for, like in one particular shape it has taken. Okay, it would explore within that green box all the possible places it will place the ligand, and it will see in which place if the ligand is showing very stable interaction, the lowest energy or the stable complex it is forming. That is what it will explore. So it will consider the centroid of the ligand inside that green box. And the violet colored box what you saw, that is outside. Now that is the place where it considers for interaction energy calculations. So inside box is generally 10 into 10 into 10. If the binding pocket is really very huge, generally for, see, whatever default option what we have provided in Schrodinger software tool is very well optimized. So 90 to 95% of the cases, everything works with the default option. But if you have information, if sometimes it doesn't work out, then you can change. So if the binding pocket is really huge, so you saw Prajwal showed you in the sitemap, only a small portion of the pocket was occupied by the ligand, and there was large empty space. If you see such type of things, you can enlarge it. So in the advanced option, you can go and you can increase the volume of the inner box so that the ligand would be explored in the whole of the space. But generally, whatever default option is there, that is more than good enough. You can just straight away use the default options.
Right. I think there were a couple of inquiries and also a lot of interest in covalent docking.
We'll be covering that tomorrow.
Okay. So there are a couple of questions that came about the hardware. I think our colleague Kishore is already responding to you in the chat. So if you have any more questions about hardware, you can just ask in the chat, and like our colleague Kishore will be able to help you out there. So I'll go for the next question. Whether more covalent interaction would lead to complete inhibition of the protein beyond recovery?
There are different types of covalent binding mechanism. There is fast reversible, slow reversible, permanent reversible. So it all depends on enzyme kinetics. So reaction kinetics drives there. Okay, so in the non-bonded reaction, it is the dissociation constant, but here the reaction kinetics which comes into picture. So whether the forward reaction is having, like, what is the rate constant compared to recovery rate constant, it all depends on that. There are various mechanisms people try out. So if the covalent bond is very strong, it doesn't break out, then it is permanent damage. If the covalent bond is not very strong, weak type of chemistry happening, probably it will recover also. So ligand can break away, it can break the covalent bond. It all depends on the reaction kinetics.
Right. So if the next question is, if a structure of protein is available for E. coli and not for Homo sapien, should we go for homology modeling before docking?
I would strongly recommend you should do that, because E. coli is not human, right? See, insulin in human is different, insulin is in elephant is different, insulin in rat would be different. Primary amino acid sequence in the protein will change. If primary amino acid sequence changes, then whole of binding site, the amino acid residue might change. So the binding interaction, what we observe, may also change. So species to species, you should be very careful, especially if you are working on antibacterials and all, you should be very careful. So E. coli is different, Bacillus subtilis is different, Mycobacterium smegmatis is different, Mycobacterium tuberculosis is different. Species to species difference will be there. So make sure the correct species protein you pick when you pick the protein.
Right. So there's a question. Is it possible to know if a ligand or a molecule will actually reach the protein? So, for example, if a protein is localized in mitochondria, how would you know that ligand would be able to go and find the protein?
That is ADME properties we are calculating. Absorption, distribution, metabolism, toxicity. In docking, we are not doing that. So those are different set of modeling things. So these are the ones which will determine the druggability of the molecule. So docking doesn't uh, target those type of studies.
Right. Okay, so there is a question about the glide score and the interaction, the positive interaction and the penalties. How are they? They're asking like, what is the impact altogether? Like, is it something like quantitative? Is it sort of, what kind of effect is that? Like, how do you actually calculate the glide score with interactions and penalties?
I showed you the glide score is total interaction energy. So when it is calculating, it will consider all the contribution coming from each type of individual interaction. So interaction coming from Coulombic or van der Waals or hydrogen bond, hydrophobic interaction, pi-cat, pi-stack. So all these type of interaction it will consider. Also, it will consider the penalty terms. So it's a empirical formula, a regression equation generated. So in the presentation, I showed you just in a simple form, just to make you understand, I have put at plus, 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 something like that. But actually, it is a regression equation. So in the manual, you can exactly check. I don't have the information now. So once you install the software in the manual, we can check that.
I think the question is more simpler than that. It's they're asking if there is a relationship between the glide score and penalties, if they're inversely proportional to each other.
The penalty terms are already included in the glide term. So any the docking score, what you see, it already considers the penalties. It will add that penalty term, and then it will compromise that whatever whether it is more or less, it will adjust that number and it would give you. So always it would be compromising, right?
Yeah, thanks, Pritesh. That's it. And I think we have 2 more questions left. Shilvia, can you take the other one?
Yeah, so the next question is, can we compare the binding of one ligand with various protein isoforms simultaneously?
You can, but docking score is not a very, I wouldn't suggest you to consider that the docking score to consider the binding of the binding affinity calculation. This is not so rigorous. So if you are running virtual screening and from there you want to identify the actives from inactive, then that would work out. So if you are looking for the isoform selectivity or fine tuning of activities like lead modification, where you want to identify the potency compared to one molecule, how much more the other molecule is active. For such cases, there are other rescoring methods. So for example, there is one tool called as Prime MMGBSA that gives you more better correlation. Okay, again, that is an empirical method. Rather than that, there is one more tool called as free energy perturbation, FEP plus we call it as. Okay, that is very accurate. So here here we get the binding affinity approximation within 0.8 kilocalorie of experimental results. So it is as equivalent to experimental results we will get, because 0.8 kilocalorie variation even in the experimental results you would be able to see. Standard error you would get within that. So the quality of the prediction made by free energy perturbation is very accurate. So you can use such tools to predict the difference between the particular isoform.
Okay, the next question, I think it was addressed yesterday also, but is metal docking possible in Schrodinger?
Yes.
Okay. I think we answered all the questions. Apologies if I missed any, which is possible. Yeah,
Shalya, I think,
Kaushik, is there any question that I missed?
yeah, there are two questions that I think will benefit a lot of people. The first one is
Okay.
from Bina Thomas, and she
Okay.
asks if you have a natural ligand, can you generate ligand library from the natural ligand?
Yes, there are various approaches. Some of the things yesterday Dr. Prajwal showed you, library enumeration or automated enumeration tools we have. So when we are taking a hands-on session, we will be discussing in detail. So please be patient. Attend future webinars. We will be covering this exactly same concept we will be covering.
And the second question is from Professor Shankar Alagon, and he's asking if inverse docking and cross docking have a similar process.
I don't know what is meant by inverse docking, so I cannot comment. Cross docking means you are taking the same ligand and you are checking it across the different proteins. So that is cross docking.
That's it. I think we covered all the questions that we can cover. Shall we go ahead?
Right. Thank you, Kaushik, and Dr. Pratesh, for your answering some of the questions. As I said, there is a possibility that we might have understood your question wrong. And if you haven't received the clarification on your questions, you can join us for our Zoom session. I think my colleague must have pasted the information. If not, you also received an email today. Please make sure that you also check your promotions tab and also your spam. Sometimes it might have gone over there. So there is a method how you can join the Q&A session, which is going to be every Thursday from 4:30 to 5:30.
So this we have called as office hour discussion. So don't get confused. So we call it as office hour discussion. So any queries, question, answer, we will be able to take up there.
And as Sylvia mentioned, the link is posted in the YouTube chat. So you can just click on the link and join us at 4:30 today.
Yes. So 4:30, we are trying to, maybe have more office hours with the need in future. For now, it is every Thursday at 4:30 to 5:30. The link is going to be the same. So make sure you save the link and do not delete the email. As also there were a couple of questions on hardware. If you missed, if we were not able to address some of your questions, please, for every hardware related question and for anything that is related to this course, you can write to us at ddcourse@schrodinger.com. And if you are interested in SOC, I got a lot of queries already. As I told, we will be discussing about it. We'll be giving you a discount code, which we are working on it. You will be getting a very good price. So do not go and register for now. The next session is going to start next month only. So please wait for that. Also, for the evaluation licenses, some of you have already sent us the machine ID. We will be actually sending you instructions how to send us the machine ID. And also we will be sharing a form with you where you need to address the questions there. You need to give us some details about yourself and the work you'll be doing. After that, we will be contacting you so that you can install and download and install the software. If you have any issues in that, also we will be happy to help you out. But do not send us machine IDs as of now. There will be a proper format for you to send us the machine IDs. We will be keeping you updated, so please make sure you keep tuning in to the live session. If you have questions, we will be able to address it only during the live sessions and during the Q&A. Other than that, you can always email it to us. We understand some of you have classes in the morning and we are trying to accommodate everybody. So for that, excuse me one second. Sorry about that. So yes, so if you have any questions, again, we have a session today on Zoom. Please, you can always join us there. If there's any other question, please email it to us. I think I'm all set. I don't have any other announcement. So I will also hang around maybe on the YouTube for some time. If you have any question, we'll be happy to answer there. For now, thank you. Have a great day, and hopefully we'll see you all at our Zoom sessions. Bye-bye.
Sir, live streaming can be stopped, sir. Ravinder, sir, if you are there, you can please stop the live streaming.
I think Dr. Ravinder didn't join today. There's somebody else taking care of it.
JSS Academy host is there, no? So
Yeah.
okay, I will leave.